All right, let's look at some special cases. We were talking about 0-1 boxes for the last couple of lectures. What is the average of the numbers in a 0-1 box? So if I have a box that has capital N tickets in all, and a fraction P of them are labeled 1, and a fraction 1 minus P of them are labeled 0, then what's the average of the labels? Well, I have N times P 1s plus N times 1 minus P times 0, right? That's the sum of all the labels. And I have N tickets in all, right? Okay, the average of the labels on all the tickets in the box is just P. Okay. Now, remember that the binomial distribution is the distribution of the sum of little n draws with replacement from a box of tickets like this. Yes?
What is the difference between the average of labels and expected value of a set?
So the question is, what's the difference between the average of the labels and the expected value? So the labels are just some particular list of numbers, okay? And we can calculate the average of that list. It turns out that what's the expected value defined to be? It's defined to be the sum of, so we have a random variable now, which is what do you get when you pull a ticket at random from the box. The random variable is the number on that ticket. The expected value is the sum of the possible numbers you can get on the ticket times the probabilities of the numbers that you get when you draw. So expected value is a concept that applies to random variables. Average is a number that applies to lists. They're analogous. The expected value of a random variable is a weighted sum of its possible values. It turns out that numerically, the expected value of the number on a draw from this box, a draw at random from this box, is equal to the average of the numbers on the tickets in the box. So that's a result rather than a definition. Right? The definition is, it's really defined to be the sum of the possible values each times the probability of those values for a random variable. That's the definition. And then it turns out that that's exactly equal to the average of the labels on the tickets in the box if the experiment is pull a ticket at random from the box.
And so they're always equal to each other?
The expected value of the number that you get when you draw a ticket at random from a box is always equal to the average of the labels on the tickets in the box. And indeed, the expected value of the sum of n draws, the sum of the labels on n draws from the box is equal to n times the average of the label of the tickets in the box. And that's true whether you're drawing with or without replacement. But again, it's a result. It's not a definition. Okay. So remember, binomial distribution is like the number of tickets labeled 1 we get if we draw with replacement from this box little n times. And we count how many tickets labeled 1 we get. And I've mentioned a couple of times that counting the number of tickets you get that are labeled 1 is the same as adding the labels on the tickets that you get. Because when you add a string of zeros and ones, what do you get? How many ones there were. Right? The zeros don't contribute anything. The ones each contribute 1. It's just counting how many ones there are. Okay, so the probability distribution of the number of tickets labeled 1 you get in little n draws with replacement from this box is So that probability distribution is binomial with parameters little n and little p, right? So let's calculate. We're going to look at the probability. We're going to look at the expected value of a binomial distribution two different ways. One is starting with a definition, and the other is using the fact that we have a box model that leads to the binomial distribution. So if we wanted to start with a definition that says this, the expected value is defined to be the sum of the possible values times the probabilities of those values, then what piece of math do we need to write down to calculate the expected value of a binomial distribution? So if we have a binomial distribution with parameters n and p. So we have a random variable that has a binomial distribution with parameters n and p. But let me back up a couple of steps. The expected value of a random variable just depends on its probability distribution, right? Because it's just a weighted value, a weighted sum of the possible values times the probabilities of those values. Okay? It doesn't depend on the outcome of some experiment. It just depends on the probability distribution. So there's no, we can talk about the expected value of a probability distribution or the expected value of a random variable. It makes sense because the expected value of a random variable just depends on its probability distribution.